All right, the second page. Let's see what we got to do here. Use the integer setting to graph this equation on your calculator. Show and label the graph, including x min, x max. That stuff, everybody, you can just do right here in your domain and range. So I've already got my equation plugged in there. You can see it on my screen. Y equals square root of 2x minus 50 plus 2. It looks like I got a negative 1 in there somehow. So I'm going to get rid of that guy. Delete him. I just don't like that little space up there. Delete him completely. There we go. And I'll go to, like they say in the problem, I'm going to go to zoom integer. I'm going to zoom and I'm going to scroll down till I see an integer. And I'll choose zoom integer. Well, it doesn't look like I got anything. So what I'm going to do now is I'm going to zoom out. So since I can't see my graph, and we'll explain why in a little bit, I'm going to assume I'm just in too close. So I'll zoom out. I choose number 3. My cursor, if you can look really close in the middle of it, is blinking right in the center of the screen. I can tap it and move it. But since I don't know where my graph is at, or I haven't shown you where it's at yet, we'll just zoom out from the middle. So I'd make sure my cursor's in the middle and just hit enter again. It's going to zoom out. And so now I can see there's something going on over here to the right. I'm going to move my cursor on my calculator screen there. You can see it kind of moving across it. And so what I'm going to do is I want to zoom into this area of interest, which is where it starts. Okay, so I'm going to hit zoom. I'm going to choose zoom in. I'm already got my cursor over there where where I'm looking, and I'll hit enter so I can really take a look at it. And you can see that this graph, and you don't have to draw this yet, okay, but this graph does something like this, okay, and this is what these radical functions, they look like. Remember, they actually are the inverses of parabolas. Parabolas look like this, and then the square root functions are parabolas that have been reflected over this line y equals x. Regardless, when we get the radical like that, we either get a top half or a bottom half. And in this case, you can see we're getting the top half of it. So let's go ahead and see how this works. Now, the original function they gave us is y equals root 2x minus 50 plus 2. And I'm going to go inside that radical. I'm going to factor it like this. Just going to pull that 2 out, and so I can see this in terms of an x minus h, because this is actually the thing that's going to control it shifting left and right. In fact, you see over here, I can't move my cursor over there, but if you look at the graph on the calculator, I'm going to move my cursor so you can kind of see right where the end and right where this thing starts at. Right? Not on it anymore. Make sure I'm on trace. Yeah, see right there at 24.89, it doesn't have a y value. I'm off of it. It really starts right there at 25 and 2.4. You could actually calculate this spot. Second, calculate, find a minimum. I'm kind of curious what it'll do. Left bound, well, it's somewhere over there, less than 25. My right bound, somewhere over here, greater than 25, and my guess is right there at the end. Yeah, it doesn't like that very much. You can't do it with radical equations. And it doesn't matter because we can see where it's going to shift, and so my drawing's going to look like this. It shifted right 25, so I'm going to mark a 25 here. It shifted up 2, and it's going to go up like that. If we want particular points for it, we could go to our second table here. And you can see I don't have any points. I'd have to get to 25 because that's where it starts. I can just go to my second table set, and I can say, hey, start at 25 for me, and go right back to my table. And you'll see now I'm at 25, and right at the top, 25, it goes to 2. If you wanted another point there, 27, it's up here at 4. Something like that. And our domain, pretty easy to answer. The x values, well, it starts when x is 2 and goes to the right. So our domain, x is greater than or equal to 2. And our range, it starts here at, oh gosh, that's 25. Sorry for domain. And we're doing domain going to the right, and that's my x's greater than 25. My range is the y stuff, and that started at 2 right here. And so it goes up. So it's greater than 2. So really your domain answers this. Hey, what's your x minimum? Well, it's right there. 25 is as low as it goes. It even says it right here. X is at least or as low as equal to 25 right there. So that's our min. Maximum doesn't have a max other than infinity. Y min, you can see it right there too, but that's right there in our domain. So that's good enough. Make sure you show that point and give its coordinates. That's a key feature of it, where it starts. Then, of course, the direction it's heading. Scroll down here to question 7. By the way, that real quick, I think I'm still kind of in zoom integer. No, it's not quite doing what it should do if you're in zoom integer. I'm going to see if I can still get it in that. Did that do it? Nope. Zoom. And trace. So I can't tell what its zoom integer is doing. Anyway, let's go ahead and move on to the next question here. Use standard settings on your graph, so standard zoom, to graph y equals e to the x plus 5 minus 3. Now this right here, and I talked about it for those of you who are in class, is called an exponential equation. Exponential equations look like that right there. And they all look the same way. And so like your parent function for exponentials is this, y equals 2 to the x. And they're called exponential. Let's write that out for you. Exponential. Because we name equations by where their variable is at, and these have the variable in the exponent spot, so we call them exponential equations. In fact, in the one we just did up here and looked at, this had the x inside a radical. Since the x is in a radical, we call this a radical equation. So back to these exponentials. I shouldn't just call this one the parent function. I should also refer to this one as the parent function of it. These are both exponential functions, but this one here, the one with the 2, this is exponential growth function, and this is an exponential decay function. Now I'm going to show you those two on my calculator here so you can see them real quick. But so you can, well, let me graph it here. So I'm going to go 2, raise it to the x power. I'll just hit zoom 6 on it. And there it is. And that's very typical to have this curve that gets really close to your x-axis or to some other line. And then it goes up, steeper and steeper and steeper. And these usually have a y-intercept that we're very interested in. And the nice thing is, like, you can generate points for this to see what's happening. This is 2 to the x. So when x is 0, 2 to the x is 1. When it's 1, you get 2. When it's 2, 2 squared is 4. And when x is 3, all of a sudden it's jumped up to an 8. And when x is 4, it's already at 16. So every single time it keeps doubling. And so it grows really, really, really fast. That's why it's called an exponential growth function. We can also put in negative values, though. We can put in -1 for x. And then we get 2 to the -1 power, which is a half. Plug in -2, and we get 2 to the -2 power, which is 1/4. And so it's getting really, really tiny as x's are negative, close to 0, but it never will reach 0. Because it's always going to be a 2 to some power, even though it'll be in the denominator and make it really, really small. Again, we've talked about this line here. That's called the asymptote. It's just a line it gets really close to but never touches. So that's what exponential growth ones look like. Let's do an exponential decay. Exponential decay ones, like this y equals half to the x. These guys do the opposite. they go like that. I'm going to show you here real quick. I will graph him right below it, and I will just put 1/2, and I'm going to type in, yeah, I'll do 1/2 like that. And it's all to the second power, so I'm going to make sure I'm raising it all to the second. It doesn't really matter because the 2, or the 1, the numerator, when you raise it to a power, it's still 1. Let's go ahead and put it in like that. We'll put our x up there. So it's clearly 1/2 raised to the x power. Zoom 6 again. You'll see the exponential growth, and here comes the exponential decay. There it is. Okay, so it decays or gets really, really small very, very quickly. And so that's what our base exponential functions look like. So what's this mean in terms of this equation? Well, if you look at it, the equation in the problem, we've got ourselves an x, and it's in the exponent. So it's one of these, either exponential growth or decay. Now, a quick side note before I forget. So it's this b value that tells you if it's growth or decay, and here's the key. If b is greater than 1, then it's growth. But if b is a fraction between 0 and 1, then it's going to be decay. It can't be less than 1. You can't have a negative exponent up here because it would, I'm sorry, not up here. You can have it up there. You can't have it as your base because if your base was negative, when x was even, it'd be a positive answer. When x was odd, it'd be a negative. So it just doesn't work. B's got to be a positive number bigger than 1 or a trap between 0 and 1. So now back to our question here. Sorry, I've gone on too long here. So is this going to be exponential growth or exponential decay? And that depends on what the value of the base is, e right here. If it's bigger than 1, we've got growth. Well, we can figure out what e is. You have a button on your calculator. I'm going to try and point to it the best I can. It's there. It says ln is the button, but above ln is e to the x. Also, if you look above the division symbol, way over to the right of the calculator, you'll see there's a little blue e. So this e to the x, let's find out what that's equal to, what e is. So here I'm going to hit second e to the x. If I want to know what e is, I'll just raise it to the first power. And e, it's called Euler's number, 2.72 approximately. But it's just like pi, it's this irrational number that goes on forever and ever and never has a repeating pattern. So this equation is a growth function because the e is a number that is bigger than 1. And not only is this an exponential growth function, exponential growths usually go right here through 0, 1. This equation, while it is exponential growth, doesn't go like the normal one does. It is shifted just like all our other ones are, left by 5 and then down by 3. Now to shift one, this is the way we do it. We say, all right, well, my normal parent function goes through 0, 1. This new one is going to be shifted left by 5. It's going to be shifted down by 3. This is 1, 2, 3. So I'm going left 5 and down 1, 2, 3. And there's my new, kind of your new quote-unquote y-intercept. Okay, so we just have to think of graphing this exponential kind of from that point right there. So I know this exponential is moving over there. I know where this is. This is at negative 5, negative 2. You can see right here, this is negative 5, and then I had to go down 2. So negative 5, 2 is where this exponential is going to run through. My axis of symmetry is normally the x-axis, not my axis of symmetry. My asymptote is normally right here, but that asymptote is going to be shifted down by 3, down to this spot right here. So there's the asymptote. And so my function looks something like this. Okay, let's go ahead and graph that thing on our calculator so we can actually see it here. So I'm going to clear this stuff out. Then we'll compare it to what I drew. Now, normally, if you guys are doing this on the test, graph the darn thing first on your calculator. So here's my graph for it. I go E, so I'm going to go second, that natural LN button. I'll put my x plus 5 up there, x plus 5. I arrow over, so I'm not in the exponent spot, minus 3. And I'll do zoom standard, which is 6. And so there is our graph, and that's what we drew down there. And we can see how it has shifted over there, and that point that it shifted to is -5, -2. Domain and range now. For our domain, let's see, we can plug in any x's, because it goes left forever, up and to the right forever. So our domain is going to be just all real numbers, doesn't have a min or max. And then our range, well, the lowest it can get to is it almost gets to 3, but not quite, to -3. And so the y values are just greater than -3, but not equal to it. And we're done with page 2. I'll zoom out a bit. And there's page 2.